Right? Last big thing that can be helpful with our alkenes is we look at the very bottom, we get degrees of unsaturation, okay? Which we did with mass spec. It shows up again. It can be helpful when you try to solve a structure. Remember, a pi bond counts as a degree of unsaturation. Okay? We have pi bonds, so we have to remember all of that cis-trans mumbo-jumbo. Okay? So we got a brief rule cut out here. Cis and trans, remember, officially is not nomenclature. It's just where are two things relative to each other. Okay? Z and E is now a specific naming system. Okay? I can say the eraser on that board is in front of me, but if I went to try and name how that eraser is connected to me, it makes no sense because it's not. Is that kind of familiar? Okay. Nomenclature. Yay, nomenclature. There's all our rules again. If you guys want a little bit of practice nomenclature, slow down because we just did a whole bunch of chemistry. You just want to be like, let's just take a break, man, chill. Little nomenclature practice. I hate nomenclature, so my answer to that is always no. Okay. So let's take a minute, see what you guys can come up with nomenclature. Didn't we do these ones?
Possibly.
We're getting some issues saying maybe, maybe not. Go ahead and try them. Okay, so we'll go through and look at just that one because I think that one is probably the biggest nightmare. I tried to color code as I went through it. I started with red. Find the longest carbon chain that contains the primary functional groups or the highest order functional groups. So you have to know the order of priorities for nomenclature. That is different than the order of priorities from Kahn-Ingold assigning R and S. It's the longest carbon chain that contains the highest priority functional group. So it has to contain the highest priority. The alcohol is the highest priority, so my numbering is going to start from that carbon. Okay? I actually skipped the numbering right away. The ene is another high priority functional group in there. So I've got the ene, I've got the all from my alcohol, and I've got the but. I then dealt with the numbering. Actually, I didn't deal with the numbering still yet. Anything that wasn't highlighted in the main chain, I circled again as a substituent and then provided the name of that substituent next to that piece. Okay, I could call that upper right-hand structure isopropyl or methyl ethyl. Officially, it has to, or sorry, according to IUPAC, it has to be methyl ethyl. Okay? If it's just general nomenclature, willy-nilly stuff, you can get away with isopropyl. Okay? But methyl ethyl is the appropriate name for that. Then I dealt with the numbering. Highest priority would be 1 with our alcohol dropped in the numbers. So the alcohol is at 1. The ene is at position 2. Excuse me. The methyl ethyl is at 2. I then have a dichloro, because there's 2 chlorines. One's at position 3, one's at position 4, and I get 3, 4 dichloro, 2 methyl ethyl, but 2 ene, 1 all. That's the last time I'll say that. The last big nasty caveat that comes with this. Can I erase almost everything except for the name? I have to recognize that that double bond does have cis-trans isomerism. So I'd split it in half, carbon versus chlorine. Chlorine takes the higher priority. Carbon versus carbon, no different, so I move out to the next highest priority. Carbon versus oxygen, oxygen has priority, so my star is on the bottom. I now cut parallel to the pi bond. The stars are on the same side of that cut, which means not cis, Z. Okay? Because cis is not nomenclature. Yes, on the same side. Yeah. Okay, so Z, where was the Z located? Position 2, 2Z, 3, 4, all that other stuff that I said I'm not going to repeat. Okay? Yes, you are responsible for that whole thing. On a test, it's probably going to take too much time to look at those pieces. So what are some big things that they might be testing on? They could be testing on priority. So you could go through and just deal with the numbering system. Okay? The other thing they'll probably test on would be E and Z. Okay? Both of those are relatively quick things to number out. Get those done first. If you have to dig deeper into the name, then do so. But get those big kind of numbering systems first and the EZ or, for that matter, R and S. Okay? The rest of them are pretty straightforward, except for the last one, which you would never see on a test, because to get the answer to that, you have to move to Rule 2.2.3, where Z takes priority over E in nomenclature. Why? Because somebody said Z is more important than E. Probably because their last name started with Z. Just a guess.
Because if they're on the same side, it's less stable than if they're on.
You could come up with half a dozen arguments. Like, really, it doesn't make any sense. So, alkene addition reactions. Remember I said we started real fast with all those reactions? Ta-da! What we see on this slide, so remember what we just talked about at the beginning where you're like, oh my god, that was way too much work, was this. Okay? This is where OChem tends to make people panic and say, well, I have to memorize everything. Understand the basics of how the reactions work. When you see those reagents, you can predict what the products are. Okay? We are narrowing down very quickly at the end of the semester. I'm not a fan of it, but memorization for what the reagents are, what they react with, and what the results come out of it, that's a lot of stuff, starts to start making sense. This is largely what happens in OChem 2, is now that you know all the basics, we just say, well, have at it. Figure it out. We'll talk about some of them, but then you should just figure it out. Okay? And that is pretty darn close to the last slide. Just kidding. Okay? So, some of the things that I want to call attention to within this. Okay? Let's take a look at the first one. Let's go clockwise. It says H2. What do you think I'm going to add to this? Hydrogen. What did I add? Hydrogen. Wow, that was creative. HBr. What am I going to add? Hydrogen and bromine. Didn't I already do that? Wasn't that what HX stood for? X being a halogen?
X is a generalization. It could be for anything.
X is a generalization, not for anything. For halogens, specifically. Don't I already have that one?
If you don't know that it's a strong.
What do you mean they're different? You're right. You're absolutely right. They are different.
I don't know how, but it just never.
The bromine's in the wrong location. Why? Because of that. You see ROR, do the opposite of whatever you think it should do. And you're probably right. Okay? What is ROR? Radicals. We'll leave that to like the last possible freaking day. Okay? ROR and light are ultimately giant red flags for radicals, and they pretty much do anything that you would expect to not happen, they do. Okay? Very limited in the amount of chemistry that goes with them, but that's pretty much how they work. After that, Br2, what do you think you'd be adding? Of course, I decided to generalize only half of this. Halogens, right? If I add Br2, I'm going to add bromines. What is interesting about the product formed for that Br2 one? Stereocenters. Okay? More important than the stereocenters, where are the bromines relative to each other? They're on opposite sides of the old pi bond. Okay? Why would they be on opposite sides? Size. Those bromines are so large that only one bromine can interact with the pi bond at any given instant, which means where does the other bromine have to come from? The backside. We get the bromines on opposite sides of that forming or the old double bond. The next reaction is doing ultimately the same thing. We're still adding bromine, yet somehow an OH shows up. Why would an OH show up? What else have I added? Water. What is water? A nucleophile. What is bromine? A leaving group. We can run effectively a substitution reaction simultaneous to the addition, and we can get that other product on there. Okay? Most people tend to go through and just memorize the results, and this is one of the things that bothers me. So we see H2O, and we say, oh, I added OH. Oh, I got to memorize another one. I added HOR, and it added OR. The chemistry is identical. There is literally no change in the chemistry whatsoever. If instead of memorizing the reagent, you memorize that the oxygen is the nucleophile and it needs to lose a hydrogen, there's one thing to memorize. What happens to the other thing attached to the oxygen? It stays there. Okay? So if you can look for patterns and similarities, you can condense the amount of content you have to memorize. Continuing around, now things get all sorts of hellish, because it wasn't hellish yet. And believe me, we aren't even halfway there. Why is this one weird? It's got mercury. That's a metal. Didn't Mike start this whole semester saying, I don't understand anything about metals? Yeah, I still don't. I just know how it reacts. Okay? So we're responsible for understanding what this reagent does to generate our product. Okay? Really, is the mercury attached to the product? No, what is connected to the product? OR. Look at the other piece. OR. NaBH4. That's a negative hydrogen to do what? Kill mercury. That's a bit dramatic. Get rid of mercury. Excommunicate. Remove it from the structure. Oh, damn, another one with mercury. Is that really another reaction with mercury? No, it's the same reaction. All that's changed is except instead of looking at HOR, I'm looking at HOH. It's doing the exact same thing as we set up with the bottom two. Okay? Extra fun one. This is probably one of my favorites. They tend to ask questions about this one. What is special about BH3? It is missing its octet. That's because it is happy with only 6 electrons. Okay? It is sp2 hybridized, which means it has an empty p orbital. And what could you place into an empty p orbital? Where did they go? Oh, they're over here. Electrons from our pi bond. Okay? And that initiates a cascade of reactions that allows the addition of H and OH across the pi bond. Why is that reagent an extra different one? Didn't I add HOH here? Why is the BH one different? I'm adding the OH to a different carbon. This is where people go through and say, well, Markovnikov and anti-Markovnikov. Okay? Ultimately, there is no difference. Markovnikov and anti-Markovnikov is only looking at the final answer and removing the chemistry. The chemistry is identical for every single one of these reactions. There is no difference whatsoever. Okay? HOR and H plus and H3O plus. You mean H and some nucleophile? H and some nucleophile? You mean H and some nucleophile. You get the exact same chemistry that we talked about at the very beginning of the class with our HBr. Right? So when you see these things, and you will see these a lot, particularly in second semester, they're called spider diagrams. Okay? What they're trying to do is condense all of the information onto one massive, nasty, ugly slide to help those students that want to memorize. Okay? The rest of what we talk about is how those reactions happen. Okay? And we try and get into some of the detail behind them. What does this one look like? I didn't talk about any of those. Oh, that's because there's more. Okay? But wait. Okay? These now, all starting with an alkene, new reactions. Why did I have to show another slide? Because I ran out of space to show all the others. Okay? And these reactions, what is always getting added to the pi bond? An oxygen. So we've increased the oxygens in our structure. That would be known as oxidation. Okay? So we have a special class of reagents just for adding oxygen to a structure. Okay? Those are oxidation reactions. Almost all of them involve weird, nasty things. Okay? Because we generally aren't good at adding oxygen nicely to things. Okay? We've added oxygen to lots of things before. You take a match. What are you doing? Adding oxygen to the particles of wood. How many oxygens did you add? Enough to completely destroy the wood. Do I want to do that in OChem? No, I want to control those steps. So all of these reactions are about slowing that oxidation process to stop at a particular end. Again, look for the patterns behind them to try and help with that memorization aspect. Holy Mother of God, is there still more? Yes, what are we doing now? Reduction. Of course, if we did oxidation, we have to adjust reduction. Okay? Reduction is now the removal of oxygen, also known as your teachers failed you if they made you memorize oil rig.
That's, yeah, we didn't work with that.
It's totally not oil rig, and it bothers the crap out of me that they do that. Leo says grr. Come on. Any case, add hydrogens. Okay? So what we will try and get through at some point this semester is looking at the adjustment to oil rig and Leo says grr to deal with how we can look at a chemical reaction. Okay? Loss of electrons is oxidation. Gain of electrons is reduction. Slight soapbox. That's way too hard as opposed to oil is loss. Loss of what? I just lost my wallet. That must mean I'm oiled? No. Okay. Yeah, see? You need that stuff. Words, man. So, electrophilic addition reaction. So here's our blanket statement that now covers everything. When we're looking at our electrophilic addition reactions, we're starting with alkenes. Okay? Alkenes, or for that matter, alkynes. And we have two reactive positions. Again, like we already addressed. We have a negative carbon and a positive carbon. We have to attach things to those. Okay? To one position, we'll attach a Lewis base. To the other position, we'll attach a Lewis acid, because they're opposite charges. Depending on the reagents we're doing, we may need two steps to add the Lewis acid and the Lewis base. Or I may be able to do it in a single fell swoop. It all depends on what kind of reaction I'm running. Okay? So, nonpolar pi bonds. There are polar pi bonds. Those are in second semester. Chapter 11 says acids. I take an alkene or an alkyne and I add an acid. What happens? What are the intermediates? What are the pieces? All that fun stuff. Okay? Chapters 12 and 24 are now electrophiles. Okay? You get slightly different dynamics between 12 and 24. That's why he split it into two chapters. 24 gets a lot more complex with the mechanisms behind it, okay, but we'll still take a look at those. Okay? Ultimately, in both cases, you need an electrophile to initiate the reaction. Why do you need an electrophile or a Lewis acid? Something needs to accept the electrons from the alkene. That's what starts the whole cascade. Okay? After that, it's now evaluating the size of each of the individual attacking species and deciding, can it happen at once or does it have to happen in multiple steps? Okay? So, pi bonds are our highest energy. That was our most reactive. Consider the balance and the structure. How do we consider the balance? Resonance. So you should be drawing out resonance structures and evaluating those resonance structures. This is where resonance again comes back and bites you. If you've been doing that resonance practice, you should be able to look at an alkene and be that one's positive, that one's negative. You don't have to draw both resonance structures. If you haven't been drawing resonance structures, you're now guessing a 50-50 shot. Yeah, that's not bad, but then that same question makes you guess 50-50 3 more times. Okay? Statistics drops your success rate on that question to now less than 20%. Okay? It's actually, I think, significantly more than that. I think it's less than 10%. I don't want you to be there. Okay? Everything in OChem is a 50-50 flip, but you're now 50-50 flipping 4 or 5 times. Okay? So you have to know what's happening at each of those stages to move forward. Okay? Resonance can help with that. So pi bonds as bases. So we'll run an acid-base reaction first and foremost to put the hydrogen on, generating the carbocation. Why can that negatively charged species not attack at the exact same instant? What is the pi bond reacting with? It's bringing in electrons. Can the negative charge of our Lewis base come in at the same time? No, we're going to get an electron-electron repulsion, which means you have to be split into 2 steps. This means when you're reacting an alkene with acids, you will form a carbocation. Do I need to be concerned about carbocations? Yeah, because what can they do? Rearrangement and resonance. Both of those things need to be evaluated when we go through and look at our alkene reactions. Right? The last thing I want to address before we leave here, do we have a stereocenter in our product right now?
Yes.
Yes. Where A is located is a stereocenter. And you're all like, what the? No, I don't want to do that anymore. You get a mild reprieve. What is that reprieve? What did A react with? A carbocation. It reacted with a p orbital, so it could have attacked from top or bottom, which means there are two products. But I only started with one thing. Where does the hydrogen go? What is reacting with the alkene, or from the alkene? More specific than double bond. The pi bond. Where are the electrons in the pi bond?
In the p orbital? P orbital.
Above and below the plane of the molecule, all addition reactions will generate two products. Okay? The most likely scenario in first semester is that those two products will be enantiomers, okay, or identical to each other. Okay? Just like we had with the substitution reactions. You get the same kind of issue popping up. Okay? So with that, we'll go ahead and end. I only made it through 9 slides, and there's literally 60, 70 more to go.